today's talk. Yeah, I'll talk about the GUD or the GUD model. I don't know how to pronounce it, but anyways, let's say the GUD model. Okay, so how can I change slides? Okay, I guess I have to do this. It's not working. Oh, yeah. Okay, mouse works. So this is the outline. I'll briefly review a few things about the diffusion models and a few things about RG flows in physics. And I'll talk about what we do in the paper and some experiments, and we could have some discussions. So this is a recent paper, and the first author is here, Matis, and he's a grad student of mine, and he'll be on the market this year. So I'll divert any question to him. No, I'm just kidding. Okay, so diffusion models. I think we all know a few things about diffusion models, but it doesn't hurt to go through it briefly. And so it's a kind of generative models which can generate all kinds of things. And we all know that there are many types of generative models. And by now, I think it's fairly understood that VAEs, diffusion models, normalizing flows, they're pretty much, spiritually connected. But today, just for concreteness, I'll talk about things mainly from the point of view of diffusion models. Okay, so what are diffusion models? So since the seminal paper in 2015 from Surya's group, there has been loads of progress, and it's been applied in various situations in science and also mainly in image generation. So there are a few things, mainly these three ideas I would like to remind ourselves of about diffusion models. So just in pictures, the idea is that first, what is diffusion? So we gradually replace the data, in this case, a cat image with noise in, let's say, T steps. So you see that in these T steps, the image gets, progressively noised out. Okay, so in particular, with diffusion, we have a tractable conditional. So condition on the previous less noised picture. So the next picture will be more noised, okay? And typically this is given by a Gaussian. All right, and so in the continuous limit, when we chop the process into infinitely many steps, this process is described by a stochastic differential equation. And for the sake of concreteness, let's take a look at this form, so which is what's called variance preserving diffusion, and we'll call it the finite variance diffusion for the reason that I'll talk about later. So what is the content of this SDE? So we have the second term describing the process of noising out. So DW denotes the Brownian motion. And then what one has to specify is this beta, which is, a function that takes value in positive real number. So you see that this is the action of this. This determines the speeds at t with which you noise out the image, okay, or the data at that point in time, in the diffusion time. So this is what we usually call the noising schedule and standard diffusion model. Okay, so this equation can be simply integrated into this simple form. So you will see that the data, let's say signal, becomes smaller with this factor alpha, which is in 0 to 1. And sigma, on the other hand, is the strength of the noise, as you could see, will increase with time. okay? And in particular, is also takes value in 0 to 1 and increases with time. So, for instance, this is such a picture taken from Yang Song's blog post. And you could see that these 4 separate images describes these 4 trajectories. So they come from different places, but then in the end, they, are samples. They resemble samples from a Gaussian distribution, namely the noise distribution. And in this case, we'll refer to it as the prior distribution, as the meaning will become clear when we consider the reverse process. Okay, so the reverse process, okay, so this SDE can be reversed in time, and which is given by this other SDE. So in particular, there's this drift term that's given by the chi-square of the distribution at time t. So we don't know this since we don't know the data distribution we started with. So this is something that has to be machine learned. Okay, so this can be done with a denoising score matching score. The score, no, that's a type of denoising score matching loss. Sorry. Okay, so in this loss, the trick is to sample to basically average over the data distribution, to draw sample from data distribution, which we have, and then S is then this score that we learned. Okay, that's you can show that the learned score, the optimum given by this loss function is when S equals this. Okay, what we need to learn. Okay, so once we have that, we could start reversing the SDE. All right, and so each step is given by, if you want this integrated SDE in discrete time, and then it's the conditional is given by the square we learned, if you want. So what we have in the diffusion generative model is basically a hierarchical generation via a Markov process. So the final, sample distribution that's learned is given by this integral, okay, over a lot of conditionals and the prior distribution. All right. So we say that it's hierarchical because there's this steps, okay, and then there's this structure. And then we'll talk more about that later. Okay, so this is the reverse SDE, for instance, in the same example. Yeah. Yeah. Actually, we should go backwards. Interesting. Is it? Okay, so anyway, so in this kind of diffusion models, as you can see, we generate the whole picture simultaneously. By this, we mean that we generate all the pixels simultaneously. There's no, distinguishing between generate one pixel first and then the next pixel, etc. Okay, because we noise everything simultaneously. We add noise to all the pixels simultaneously. Okay. So this is to be contrasted with autoregressive models, where we generate one token at a time. And later, what I'm gonna tell you is how we try to conceptually bridge or interpolate between the two forms of generation in our model. Okay, so before we get into that, let's have a quick review on RG flows. So since this audience have all a background in physics, so I'll be extremely brief on that. So what is an RG flow? As we all know, we can do physics thanks to the fact that there are separations of scales oftentimes in physical problems. In particular, when we have Wilsonian RG scheme, it is a scheme that we use to erase the short distance information that we don't care about while retaining the long distance information that we do care about. Okay, so what does it have to do with the diffusion model that I was just talking about? Well, the diffusion process is somewhat like an RG process. And this can't be made very precise by, I'm now like explaining the footnote here. This can be made very precise by, let's say, comparing the Fokker-Planck equation and making certain choices, for instance. And there's also recent works on that. And then this idea of using diffusion to do RG can also have practical applications in physics. For instance, it has inspired some RG schemes. But since this is not what I'm going to focus on, so I'll be pretty hand wavy about the connection instead of going to the math and basically just be spiritual about it. But this connection in its detailed form can be, the topic of another talk. So, okay, so spiritually, or heuristically, what's similar about the two kind of process, the diffusion process and the RG process, is that first of all, there is certain process of information erasure that's happening, and second is that there is universality. So let's explain that a little bit. So information erasure is quite clear and manifest when we look at RG, for instance, on the lattice real space RG. So the process of real space RG oftentimes involves, for instance, you take a 2x2 block of spins or whatever other degrees of freedom you have, and then map it onto, just a 1x1 block. And in this way, you make the lattice spacing coarser, okay? And clearly you lose information. You lose the high energy information by doing so. And of course, it's important that you choose this map wisely. For instance, you have spin decimation, a majority rule, etc., etc. There's whole topic on this process, but the lore is that once you choose this map reasonably, and then you're sort of doing the right RG thing. Or we can look at that from the field theory point of view. Take, for instance, the Pochinski RG as an example. So in this process, okay, you have an effective action that depends on your cutoff scale. So one thing, for instance, what this cutoff scale does is to cut off degrees of freedom, and this can be seen by this insertion of 1/k in your propagator. Okay, so k is your momentum. So I've gone to the Fourier space at this point. So this k of lambda is a cutoff kernel, which has to have the property that it's 1 when k is much smaller than the scale lambda, and approaches 0 when k is much larger than lambda. So there's this. So oftentimes, for instance, is chosen to be some kind of a sigmoid. So you have the parameter a that tunes how sharp the cutoff is. All right. So as promised, I will not go into the detail of comparison between Pochinski RG and diffusion, although this can be made. So And so instead of doing that, so let's go to the second point, which is universality. Universality, of course, in physics plays a very important role. So we have families of theories with different UV properties, but they all flow under RG to have to the same fixed point if you want. So, okay, so what are these two things on the diffusion side? We see that there are some similarities, but there are also differences. Okay, so on the diffusion side, the information erasure happens because we add noise to, in this case, the picture. But it's a little bit different from RG because in RG, we eliminate degrees of freedom from high to low frequency. We do this with an order. So with diffusion, we just throw noise at a whole, you know, at every pixel at the same rate. Okay, so there's, how about universality? So in diffusion models, okay, we also have universal behavior because whatever picture you started with, it's replaced by just a noised picture or, by a sample drawn from the prior distribution. And here in the RG case, this universal distribution is replaced by some fixed point action, the so it's a little bit different. So, okay, so this difference will later inspire us to take a closer look at the diffusion model. So before doing that, I mean, just be more, going further into the heuristic direction, we could also see that heuristically, hierarchical generation is somewhat like inverse RG. Hierarchical generation is very powerful, right, in all kinds of machine learning applications. So here I again take the example of generating images from small images and then condition on that you generate a higher resolution image and so on. So it is literally somewhat like the inverse of doing real space RG. Okay, so the idea, well, here is what? Why does this hierarchical generation, why is it useful? Well, because there's oftentimes a lot of structure in the data and you want to exploit that, right? So, or to put it in another way, like data sets, they're often learnable because there are some kind of structures and oftentimes hierarchical structures that they have. And for instance, in natural images, we know that there's this famous, sort of approximate scale invariance. Okay, so this is to be compared with, for instance, the amplitudes of scalar field theories. So understanding and leveraging these hierarchical structures oftentimes leads to better generative models. So can we analyze this in the framework of diffusion models? Okay, so we're done with the background. Now I'm going to explain what we do in the paper. So, okay, so this comparison between RG and diffusion was one important, lesson for us to start considering these three choices we have made along the way of building a diffusion model. The first is the basis. Why the basis? We see that in RG, the information erasure process is more conveniently described in the Fourier space. However, here in diffusion model, we usually, you can use a latent space or whatever, but there's no there's typically less discussion about which basis to use when you erase information. And then the second thing is It's just the basic fact that in RG, your information erasure is happening in the way that's manifestly sort of ordered, right? You first do, in the case of a sharp cutoff, you first erase one frequency and then you move to the next and so on and so forth. And in between that, you renormalize your couplings and so on. So here, why not also give diffusion model this degree of freedom to tune the level of your noise at a given time for a given, we call it component, okay? It can be a pixel or it can be whatever, depending on the basis you have chosen. And the third thing is, okay, so in RG, the final distribution is given by your fixed point action. So why we always need to choose the isotropic Gaussian here? Well, is there other choices? Can other choices be better? Yeah, for instance, you could choose the fixed point scalar field action. It's the free scalar action here, for instance. Okay. So to discuss more concretely how these three choices enter in diffusion model, so let's go back to the equations. And so in the next few slides, there will be some equations. So let's go back to the beginning and start with a general SDE. Okay, so again, DW is some white noise in the process. Okay, this is general enough. But now we want to specialize a little bit because we still wanted to have certain, convenient structures. In particular, we like to have a diagonalizable Ornstein-Uhlenbeck process that's described by this by this SDE. So first, we choose a specific form that this little s is basically linear in phi. So that would describe an Ornstein-Uhlenbeck process. Okay. And second is this word diagonalizable. So we choose a simultaneously diagonalizable F and G. Okay, F being this matrix, right? So in particular, we would say that it's simultaneously diagonalizable by this matrix M. So in particular, it would be useful to decompose this M into two parts. One orthogonal, just rotating your frame, and the other is a scaling. So in particular, S will be a diagonal matrix. So once you put in that, indeed, you see that what you have is a decoupled SDE in another basis that's given by this M, okay? It's just a linear transformation from the original space. Okay, so, funny, that's, okay, this is the slide. So in particular, you see that the diagonal basis is this chi is basically determined by U, this orthogonal matrix that rotates the basis. Well, I mean, of course, it doesn't have to be linear in general, but let's postpone that. So this, you could do your latent space or whatever, and then this step would be then coming on top of the latent space. Okay, so in terms of the original basis, you could see that now you have also changed, the distribution, the variance, the covariance of your prior. Okay, so your prior distribution will still be a Gaussian, but now with this covariance matrix, and in particular, the variance of each component will then be given by this scaling matrix S. Okay, so if you can think about the scaling S as determining the prior you choose. Okay. And finally, now we have all the freedom to choose a different beta, so the noising speeds for each component. So this choice of beta will beta now is a vector. Okay, it's a d-dimensional vector. If your data is lives in the d-dimensional space. So this will be our component-wise noising schedule. Okay, so you will have like one beta for 1 degree of freedom, one noising schedule to be 1 degree of freedom. And we would like to stress again that for any of such choices, okay, the forward SDE retains a simple form and decoupled form that's describing an Ornstein-Uhlenbeck process. So all the benefits of diffusion model, like being analytically amenable, still remains, no matter what the choices you make here are. So for concreteness, we'll again focus on finite variance diffusion. So that means that this scalar f tilde will take a specific form here. Okay. So now I'm writing down this simple decoupled SDE in my new base, a rotated basis cut. Okay. So then again, as before, we could just per component integrate the SDE and then have the simple form. Just everything the same as before, but now instead of having one universal alpha and sigma, the noising uh, the noise variance for all different degrees of freedom, you have one each individually, okay, for each degree of freedom. In particular, you can see that it is indeed finite variance as usual. You can compute the variance and it's going to be given by the original data variance, okay? And it interpolates between the data variance and 1, okay? Because remember that alpha squared and sigma squared adds up to 1. So one quantity that we find particularly useful is the signal to noise ratio that measures how much information is retained in each component. Okay, and it's so we take the literal definition of signal to noise ratio. So there is a factor of the original data variance that goes in front, and then this ratio between the signal factor and alpha I and the noise factor sigma I. Okay. So, okay, so now this is about the 3 choices and a few brief words about how this can be learned. So straightforwardly, I mean we could again write down the reverse SDE as before in exactly the analogous way. And then we now need to learn the score. So fortunately, the usual score matching loss function can be straightforwardly generalized to this case when you have different speed of noising, different degrees of freedom, because it just factorizes into a sum. So you could choose a weighting factor for each different degree of freedom if you want. And also that takes some generalization and innovation in the network architecture, in the sense that you have to allow for your to be learned score S to be conditioned on the noising state of each component. Okay, so once you do that, you can start to train this model. Okay, so now I have told you like what are the new sort of choices that you could have in this GUD model. So let's now discuss how to make these choices and what choices are particularly interesting to us. So let's start with the basis. Okay, so you could do things as usual. So meaning, you could do things in this image case in the pixel space. So, or it's one thing that's obviously interesting is a PCA space where, your data variance is already diagonalized, or drawn, again, inspiration from RG, and also relying on the fact that, for instance, in some data sets like the natural language, for the natural image data set, you have this approximate scale invariance. You could go to the Fourier basis. Or other bases like the wavelet basis are also very natural for hierarchical generation. Of course, if you have a temporal data, you can choose the temporal basis. For instance, if you have like a spectrogram and so on. Okay, so we're going to try them out later. And the second choice I'd like to talk about is prior. So namely, what kind of noise you add to the data. So you could do things as usual as in the standard diffusion model, namely you just use isotropic Gaussian. Or looking at the time evolution of the variance, we see that interpolates between the data variance and one, right? In the case, so what you can actually choose is to have basically you rescale your data such that the data variance is one that can be chosen by choosing your scaling transformation S, such that the variance is really constant throughout time. Okay, so in the original basis 5, okay, if you like that point of view, that amounts to choosing a prior that fits that matches the variance, the variance of the data. Okay, so you could still have a Gaussian distribution, just have the variance completely matching that of the data. So in some sense, in physics language, it's like you already put in the 2-point functions of your data. So what you have to learn in the process, of learning the square and so on is only the higher point function. Okay, so you can think about learning the diffusion as sort of turning on the interactions, if you want, from this point of view. So so that's also an interesting choice of prior. We'll call it the sometimes the unwhitened and whitened for hopefully obvious reasons. So that's from a chi point of view. So visually they look quite different. So this is noising the process of noising out the same image. So with no learning involved. Okay, the only thing that changes is the choice of prior. So the first one is a picture of the standard diffusion, and the second one is when we choose a variance matching Gaussian. Okay, so that's the picture. And then we go to maybe the most interesting choice. So how do we choose the component-wise noising schedule? So as I mentioned, we can tune an individual path for each degree of freedom, okay, of sigma, what we call the noising state, which starts at 0 from the beginning of the noising process, okay, and ends at 1 at the end of it. Okay, so now it's a vector. So alternatively, it just also gives a different evolution of the signal to noise ratio for each component. So you can tune sort of how fast you want the signal to disappear, or in the reverse direction, how fast you want a degree of freedom to be reconstructed, or to be constructed in a given degree of freedom. Okay, so in picture, so you have a path. So this is a picture in the space of distributions, if you want, with your prior chosen. Okay, so it becomes a point in the space, and with your data set chosen, so the starting data distribution is also chosen. So by choosing different component-wise noising schedule, you are choosing different paths to go from the data distribution to the prior distribution. So note that this is very different from the discussion of noising schedule in standard diffusions, because actually they all amount to the same diagonal paths, right? Because you choose all the sigmas to be the same for all degrees of freedom. So in the discussion of noising channel in standard diffusion, is actually the discussion is actually about different time parameterization of the same paths. So here we're really talking about taking a different path. Okay, so to turn it around in the generation process, the different paths, what it amounts to is different orders of generation, right? You could, for instance, in the physics data, you could choose to generate, let's say, the high frequency degree of freedom first, and then you try to condition on that, generate a low frequency degree of freedom, but we know that that's intuitively bad, right? We want to generate first the low energy degree of freedom and condition on that, generate the details. So yeah, so for certain data sets, we have intuitive sort of understanding of what path should be better. Okay, so let's look at some examples of different paths you can take. In the standard diffusion sort of this curve, okay, of the noising state evolution is identical for all degrees of freedom. So it's just one curve. So you can make things autoregressive by just choosing this kind of curve. So so what it means is that you completely noise out 1 degree freedom before you do the other one. So in reverse, you first completely sort of generate, if you want, 1 token before you generate the next one condition on the previous one. Okay. So in this sense, we say that by allowing component-wise noising schedule, you can make a bridge between standard diffusion and autoregressive way of generation. But of course, now you have, okay, so this is the explanation of that. So in this comparison, when you completely noised out 1 degree of freedom, and it's the same as you maxed out that token. So that's how we make the analogy. And of course, you can make that very sort of explicit and just implement this. Yeah. So of course, now you have like infinite room to play between them. So this is what we call soft conditioning. Okay, so you generate 80% of 1 degree of freedom first, and then when you start to generate the next one, and so on and so forth. So again, it's a Markov process. It always depends just on the previous time step. But the previous time step can contain sort of 80% of information of one degree of freedom, 50 of the other, and 20 of the yet another. So this is what we call the soft conditioning. So okay, so that's the idea of all the degrees of freedom we have introduced into the game and all the possible choices we're thinking about making. And of course, now you could test it, all kinds of things, but because of time and compute, we make a selection that's of things that we will show you now. Okay, so this is a list of things we have tried and then classified by these 3 different kinds of choices. So okay, so the A and B is the counterpart of the both picture I've shown you. So where we're showing what we're showing here is a different choice of prior. So isotropic Gaussian like in standard diffusion and various matching Gaussian like this, which is B. Okay. And then we also choose a basis that's just column, so that corresponds to column-wise generation. So that you see in picture C. Okay, so you generate one column before moving to next. And then D is, I hope you could see, is you column-wise do it, but so you decompose it into the wavelet basis, and within the wavelet basis, you do it column-wise. So that's D. I hope you could see that structure. Okay, so for instance, so what's the result? So this is some very preliminary test results. So here, what we're showing is that, remember, the degree of freedom is infinite dimensional because that amounts to choosing a path between 2 points. Okay, so it's an infinite dimensional space. But we take a slice, a one-dimensional slice over it, which is parametrized by A. So this slider corresponds roughly to how how autoregressive it is. Okay. So or softness, So when A equals 1, it's the standard diffusion. Okay. When A equals 0, then it's the least autoregressive in some sense. Okay. And we also try out the different choices of prior. So the isotropic Gaussian, the original one, the usual one is blue, and then the orange one is the variance preserving. And you see, first of all, that in terms of the negative log likelihood, it seems like the usual noise is better, but in terms of FID, it's swapped. And okay. Before I say too
Miranda,
much
can I ask a question?
Yeah.
At the previous slide. So, I mean, when you make those measurements, those performances, that's for certain architecture and hyperparameters. So the fact that it seems optimal when A is 1, is it because those hyperparameters were chosen, for the usual diffusion, were optimized there? Or is it?
That's one possibility, but there seems to be something about it. I mean, and also I would like to stress that it is also pretty much dependent on the data set.
Okay, but what you're doing is looking at some architecture unit used in the field with hyperparameters. I mean, oh, sorry. Did I lose you? Can you hear me?
We can hear you, but I think Miranda froze.
Okay.
But I mean, if you want, I can say anything
Yeah,
about
please,
the model
please.
that we used.
Take over.
So we didn't do hyperparameter tuning in that sense. So we basically based our architecture on the unit that is used in. Oh, I guess now we lost also the visuals.
Yeah.
That is used in other work. So there's the possibility that some aspects of that architecture were chosen to work especially well for that point.
I see.
So that would
Okay.
be my answer, but it seems to be robust. So we tried various different things and slightly different permutations of architecture, and it always worked quite well for the standard diffusion.
Okay.
I don't know
And
how long Miranda would be gone.
if
Yeah.
Miranda is gone, can I ask also, how do you measure this negative log likelihood in high dimension like that?
Yes, so we do what other people also do, which is to so generally if you have an SDE, you can find in this case also an ODE version that has the same Fokker-Planck equation. Right? That's quite well known about diffusion models. And in that case, you can, in principle, compute the change of density if you know the divergence of the vector field. And that's obviously computationally expensive to do. But we can estimate that with the Hutchins trace estimator for the trace of the Jacobian. And so it is still expensive, but you can do it for evaluation purposes.
Okay.
Does that make sense?
Yeah, thanks.
So Miranda should be joining, so we will restart soon.
Yeah, I'm here again. I don't know what happened. Sorry about that. I think Zoom crashed on my computer. Don't take it personally, Mathieu.
So your questions were answered by your student, so it's perfect. You can go on.
Okay, awesome. All right. So I should yeah, try to share my slides again. All right, so are the slides back up? Yeah. Okay. All right, so here we see you know, an experiment done in the Fourier spaces. And then we take a two-dimensional slice from the space of possible schedules. So one, again, tuning sort of the softness parameter, and the other one, well, it's a bit hard to explain, but we tune a little bit like the spacing between different degrees of freedom, how close by they are in terms of their noisy state, roughly speaking. So the zoomed in region is this, and the standard diffusion point is the black dots. So the optimum is still pretty close, very close, I think, from a standard diffusion. This is again for cipher 10. So okay. And then I'm going to try to, okay. And the next slide, you can see by choosing a column-wise basis, we could do what you could play with is to have image extension application. So since you have a column-wise schedule, so you generate one thing and then condition on that next thing and so on and so forth. And then you could just keep, you know, a slide your square to the right and keep doing that. So this is the image extension. Basically what it shows is that these preliminary experiments show is that first of all, okay, it still works. And second, that making these choices do sometimes make a difference for bad or for better or worse. And standard diffusion is pretty good among all these choices, but obviously there's a lot of room out there to optimize. Okay, so what we're thinking about playing with, working on is
Miranda, I had a question about the image extension. So I think it's really cool that you can now interpolate between autoregressive generation and diffusion models. So I'm wondering if you can make the image extension results look better by comparing them to just purely diffusion models. So you can do, for example, image infilling, right? Where you just specify the left edge of the image and then let the diffusion model do its work and condition on the left edge and then fill out the rest of it. Does your column-wise image extension do much better than that in some sense?
Yeah, actually we haven't made that detailed comparison yet, but that would be indeed very interesting. Yeah. We're applying for more compute. Yeah.
Okay, thanks.
Yeah. And okay, so one thing that's I think very interesting that we've been thinking about a lot is how to do optimization, how to choose the make the optimal choices. Okay. And so we're looking at it from different points of view. And then obviously other types of data sets. I mean, for instance, we also played with physics data set, which, I mean, they behave differently. And obviously it'll be really interesting to just try this kind of idea on, natural language processing. And then I heard that now, I read that now we are supposed to add at least one slide to discuss our possible connections. So anyways, this is the end of the normal part of the talk, and then I could describe a little bit what I see as possible connections. And I think, for instance, very direct connection is with Mathieu's lecture a couple of weeks ago on learning hierarchical representations. So more concretely, so they also look at this phase transition of when, phase transition happens when you do this forward backward experiments in diffusion models. So here, the question is when this phase transition happens in diffusion time. So in our language, right, that is adding noise at the same speed to all pixels. And so that corresponds to a certain, a certain point on that particular path. But now you could tune your path. You could, for instance, ask yourself, if I just, noise out a group of degrees of freedoms, and when do, where is phase, for instance, phase transition happening when I just focus on 1 degree of freedom? So I think that's a fun question. And then okay, so that's it. And then I also mentioned that we also put out another paper in another direction, so which is what we've been working on applying normalizing flows for lattice gauge theories. And we've also been talking with Eva's group, like Bruno here, and looking into ways that this work we've been doing can be combined with their novel sampling methods in the context of lattice gauge theory. So, okay, with this, I'll finish my talk.
Thank you, Miranda. Are there any more questions?
I have one, if can I?
Yeah.
So Miranda, I was wondering, in terms of theory, what do you think would be simple models, maybe of synthetic data, to understand which path in your diffusion model, or to understand if, autoregressive versus the usual diffusion model, which one would work better? And Yeah, I mentioned that to you, I think, but I mean, I know one nice work about that by Clément Angler and others, where they compare two kinds
Yeah.
of autoregressive models where you learn languages reversely or in the good direction.
Yeah.
And then you find systematically, I think, in all languages that
Yeah.
it's better to learn languages as humans do. I mean, as humans read it.
Yeah.
And they have a nice model for that. Like if you show as a data set, multiplication of prime numbers,
Yes.
it's clear that in terms of hardness, it's much easier. In polynomial time, you can actually, make a multiplication. But if you have to go backward, it's actually much harder to factorize prime. So I was wondering, I mean, this question of going left or right, you're sort of generalizing it. You can go in many different paths to this question. I mean, factorizing prime numbers, you could do the diffusion way of thinking about it, but more generally, what do you see as ways to tackle this question theoretically of, for what kind of data, which path would be better?
Yeah. Yeah, so now we're thinking about it more just if you want abstractly, not being sort of just thinking about it as finding the optimum path between two distributions, but restricting yourself to the subspace that can be reached by a diffusion process. So not leaving that subspace. So that's how we are thinking about the optimization problem in terms of schedule right now. So yeah, but indeed that yeah. So the hope, of course, from that kind of thinking is that your correlations and hierarchical structures within the data set can be captured by that kind of optimal path description. But that has to be tested out, I agree.
But how
But
are
to
you
test it,
defining, sorry, how are you defining optimality? Just like which model does best on a particular data set, or?
well, I mean, so there's interesting work these days on optimal transport and that.
Right.
So
So I
that's the
think,
kind of optimality.
yeah, so I think diffusion follows some kind of gradient flow on the Wasserstein metric, right? So isn't diffusion optimal, like the going to an isotropic Gaussian, or? I mean, I guess it all depends
Yeah,
on what you mean by
yeah.
optimal. Do
And
you
also that
that's
depends on all sorts of things. Like for instance, in which basis you're doing the diffusion, right? I think.
right.
So that changes the setup of the problem, not particularly the solution of the problem. So there's a few pieces to optimize there. So, but yeah, yeah.
I mean, maybe I can say, I mean, in terms of this literature I know about, I mean, they were using large language models and asking, do you learn better from the left or from the right? So that's conditioned to given kind of transformers architecture, but they look at the modern one and they were just asking practically which one, for usual training procedures, which one has the best tester at the end.
Yeah, so indeed, I mean, the problem you raised is a good one, right? Because you could have theoretically the best one, but I mean, yeah, you also have given the architecture, what is best, or even given the hyperparameters. Yeah.
I also have a question, Miranda. So have you tried using this soft conditioning idea for language? You say something towards the end about, can you say more?
Yeah, that would be one interesting data set to experiment on, but yeah. But I mean, I think at this point, we're not focusing on building a better language model necessarily. Yeah. but just as a data set to test the idea.
Mm-hmm.
Right. I think there's no more questions, so we'll stop the recording here. Unless somebody has a very pressing question.
My name is Miranda Cheng. I do research.
Who was talking?
There must be a mistake,
Yeah, okay.
I guess.
Registration then.